right, good morning, good afternoon, good evening, ladies and gentlemen. Welcome to this series of online lessons. If you haven't already, please subscribe to the channel and leave a like for this very lesson. And compliments of the season. We are in the festive season, and basically, this will be the last video for the year 2023. And yeah, so we're going to look at linear transformations. Then from there, I hope to develop the lesson further. But for now, I'm just going to introduce linear transformations and what they are about. Let's enjoy. So basically, when you talk about transformations, we're just talking about being a particular definition, and when variables go through those definition, which is more like a machine, think of it to produce some image the other side here. So when these variables go through this machine, they produce some other variables right here. So now these variables that are produced outside here, we can call them the image. And what goes into the transformation function, we call it so this is the image orange, and these are the object, and basically this is the definition that is governing the transformation. So basically, when objects go through a particular definition, they are transformed and they produce an image, which is what we have here. And basically, in linear algebra, we are going to be determining if the image produced here is linear or not. Okay, so we'll be given a definition. So for instance, I think I should is defined, let's by transform 3x, y, and z. What you get is 2x more. Is this a linear transformation? Okay, so for instance, you have a question like this: given a transformation that changes vectors in 3 dimensions to vectors in 2 dimensions, which is defined by this transformation. When you get 3 vectors x, y, and z, it becomes 2x comma y. Is this a linear transformation? Now, if this is a linear transformation, there are only 2 conditions that it should satisfy. So that is, if this is linear, or if t that transforms vectors in 3 dimensions to vectors in 2 dimensions is linear. So this goes for all transformation. The first thing is the transformation of vectors belonging to R3. You can transform them individually. You should get is the same thing as the transformation of the 2 vectors combined. Okay. Secondly, you transform, or if you transform alpha and a vector from this definition, it should produce alpha times the transformation of the vector. So that is basically what we are going to be doing. So any definition that is linear should satisfy these 2 conditions. If one of these conditions are failed to be satisfied, we conclude that the transformation is not linear. And in short, we can combine these 2 conditions into one. Basically, if we want, we can just use the condition transformation of alpha u plus v would be equal to alpha transformation of u plus transformation of v. Okay, so we can use these two conditions, or we can just use this one condition that combines the two conditions, right? So let's determine if this transformation is linear. So first of all, we're going to get two vectors in 3 dimensions as suppose. So the first vector here is representing the object, and what is produced here is the image. So we get two vectors in the object. So we say let u equal to any vectors in 3 dimensions. So we can say, we can even use the first one, which is x1, y1, y, z1. Okay, and another vector v in the object, we'll say x2, y2, z2. Okay, and basically the transformation is such that when you transform vectors in the object, that is x, y, z, what you're getting is a vector in 2 dimensions, 2x, y. Okay, so now we'll start with the first condition. So let me say first condition, let me use this one. Condition 1, transformation of u plus v should be equal to the transformation of u plus the transformation of v. So we can start with either side. So if we start with this side of the equation, we need to produce this other side. That is the goal here. So we'll say transformation of u plus v will be equal to the transformation of, we get our vector u, which is this one, which is x, y, z. So x1, y1, z1. Then we add it to v, which is this one, x2, y2, z2. So we add them up. So we add them. Let me start from here. So adding them, we're going to have transformation of, so this is representing x1 plus x2, y1 plus y2, z1 plus z2. Okay, now we need to transform this. So basically the definition is saying, let me just highlight the definition. The definition is saying if you have x, y, and z, so meaning that this whole thing is representing x, this whole thing is representing y, and this whole thing is representing z. When it is transformed, you just get 2 times the x part. So the x part is this column, so that is the first part. So we just get 2 times the x, which is this. So in this case, which is this. So this is 2 times x1 plus x2. Okay, then you get the y part. So the y part is this. So in our case, the y part is this. So which is y1 plus y2. Okay. Okay, so we can close that like that. So now we can distribute. So we can distribute the 2 here. So notice that the transformation sign, the t here, has disappeared because we have transformed this vector. So now after transforming, we distribute the 2. So the 2 distributed, we are going to have 2x1 plus 2x2, then y1 plus y. The goal here is to separate the x1s and y1s on one column and the x2s and y2s on the other column. So we can say this is equal to, so we can say this, so we'll say this will be 2x1 y1 plus 2x2 y2. So basically when we add these two, we're going to have that. So if you notice, this is actually the transformation of u, which is equals to transformation of x1, y1, z1, you notice that when we transform u according to this definition where we get 2x, so in this case it will be 2x1, and y1 is basically this part here. Okay, and transformation of v is basically this other part here. So transformation of v, which is x2, transformation of x2, y2, z2 is basically equal to 2 then times the x part, which is x2, then comma the y part, which is y2, which will be this. So this basically is equal to transformation of u, which is this part. So this part is the transformation of u plus this part is the transformation of v. Okay, so therefore proving that transformation of u plus v is equals to transformation of u plus v separately. So we say therefore transformation of u plus v has produced for us transformation of u plus transformation of v. Okay, so first condition has been satisfied. We can go with the second condition now. So the second condition is right here. So transformation of alpha times u should be equal to alpha times transformation of u. So we pick one side and one side should produce the other side. So we know that transformation of u is basically equal to 2x1 y1 gotten from here. So transformation of u, which is equals to transformation of x1 y1 z1, will give us this right here. So we know what this is. So now what we're going to do is we're going to say transformation of u, this will be equals to transformation of alpha times u. So u is this vector right here. Where is u? Just span it down. So u is this one right here, x1 y1 z1. So alpha times x1 y1 z1. Okay, we multiply the scalar here, so we still have the transformation there. The scalar will be alpha x1, then alpha y1, alpha z1. And now we need to apply the definition of the transformation. So we need to transform this. So according to the definition of the transformation, which is right here, I hope you can see that. When you have vectors x1, y1, z1, or x, y, z, you just get 2 times the x part. So the x part is this. So it will be 2 times this. So basically we're going to have open brackets 2 times alpha x1. Then you get the y part. So the y part in this case is this part right here, so which is just alpha y1. Okay, and basically here we need to factor out the constant alpha. So factoring out the constant, so we see that the constant is on both of these, so we can factor out alpha, and we're going to have 2x1 and y1. So basically this is this right here. So we can say this is basically equal to alpha transformation of u. Then therefore we can conclude now to say transformation of alpha u is equals to alpha transformation of u. And you make a conclusion. You say since the two conditions of a linear transformation have been or has been satisfied, T that transforms vectors in R3 to R2 is linear, the linear transformation, right? So that is basically how you approach such a question. Right now, I'll do more examples in the next lesson, but for now, this is about it. So let me just run through the whole lesson. So basically, we are given a definition in most cases, and we have to determine if that definition is a linear transformation or not, right? So if that definition is a linear transformation, it should satisfy these two conditions. Okay? When you get any of the vectors in the object is in R3 in this case, and you transform them individually, this should be the same as adding the two vectors from the object, which is in R3, and then transforming them. Okay, so which is what we did here. So we added the two vectors in the object. The object is R3. So the object is R3. So we got vectors in R3. We can name them any vectors. So these vectors are in R3. And we added them, then we transformed them. Then it should produce to us these two vectors, which is the transformation of the individual vectors. Same applies, you can multiply a scalar to a vector in the object. So the object is in R3. So we multiplied a constant to a vector in R3, which is x1, y1, z1. And we transform it. When we transform it, we're going to have this. Then now we need to factor out the alphas so that we see if we're going to get the transformation of U. Okay, so that is basically it on linear transformation. If the two conditions have been satisfied, then the definition is a linear transformation. If one of the conditions failed to be satisfied, then the definition is not a linear transformation. All right, have a good evening. See you next year.